The share.
Exato.
Shallow e juntos?
Shallows and juntos now?
Essa ficou ótima. Precisa pôr um pôster com esse título. Shallow e juntos não é ótimo. Realmente é o fim da linha. Realmente.
Eu pedi aquela carta na secretaria, mas não quem será que tem aquela carta?
Tem um diretório no
Ah, não, quem está preparando é
na
o
área de
diretor,
trabalho,
Porque
que é o workshop
Você
Fátima.
ser logo?
Não,
tinha ninguém,
workshop,
não? Eu
volta.
fui lá na secretaria, não tinha, não
Esse aqui,
estava
ó.
a secretária.
Aqui
Aí.
você fala no departamento?
No departamento. Então, ninguém tem essa carta ainda pronta para
Não.
levar.
Não tem pronto. Porque tem que passar. Porque, bom, burocracia. Mas vai ficar pronta bonitinha. E agora, qual que é?
Porque aí eu preciso também passar por outra burocracia
É lá.
para que me deixem colocar o computador na rede, não? Então tem que levar um patrimônio de...
Eu vou ver se eu acrescento.
Tirei o certo.
Não tirei o
Depois
certo.
algum software da Unicamp, então tem que ter
Entendi.
o
Não,
patrimônio
eu vou apressar nesse.
Agora não tenho computador, aquele vinha que
Não, você precisa ter usado. Eu vou fazer isso. Eu pedi para ele.
Agora é férias, né?
Sumiu. Não é fácil, não.
Eu estava brincando com ele. Só eu que fui submetido a tudo.
Não sei. Oi? Eu falei pro Prachan até 2h15, que acho que ele deve ter ido no banheiro, não sei.
Eu acho que
15.
bom, tem que dar um limite um pouquinho. Porque também a gente depois, uma parte da discussão do projeto temático, a gente abrevia.
Uhum.
Entendeu? Até porque é mais coisa geral, não é resultado, né?
Uhum.
Então tudo bem.
Então, mas acho que na apresentação última a Regina falou que talvez o Landulfo apresente tudo, não precisa de todo mundo apresentar. Mas acho que a gente pode começar.
Eu acho que é melhor.
Aí? Não vai?
Eu acho que é bom, porque tem um pouco mais de resultado. A gente apresenta uma coisa mais geral e você já apresenta um pouco mais de resultado. Eu vou fazer o seguinte, tem uma coisa que eu vou fazer 3 slides com essa coisa inicial, né? O que é? Eu vou fazer um negócio assim, mostrar o objetivo, o projeto, ok? Aí, entendeu? Pronto. Aí cada um, tá?
Deixa eu botar no modo avião aqui, porque vai que alguém resolve.
Será mais 5 minutos, viu? A família voltar mais.
E hoje tem vinho, não?
Eu não sei. A minha me falou, e aí, tem vinho na varanda? Porque não tenho coral hoje. Eu falei, não sei, não conversamos nada sobre isso. Aí depois a Mary falou, mas vem aqui jantar com a Benevides, eu fiquei
Ah,
sabendo
bem.
que ela vai viajar, né?
Sim.
Ela vai para Europa.
Hum.
Aí eu falei, Neide, vê se você vem aqui, porque se ela vier, daí a gente pode se reunir lá em casa. Agora se ela falar não, eu estiver aqui na casa dela,
Fica
aí não
difícil.
rola. Mas vamos ver, falei, mas ela não me respondeu. Falei pra ela vir lá em casa, porque daí a gente pode. Mas se não for hoje, de repente amanhã a gente faz alguma coisa, né?
Hum?
Comer pizza é bom, comer pizza é bom, engorda bem.
Pode, pode. Então, eu quero ver se pelo menos dois deles fazem.
Fazer sim.
É.
Eu dei uma cutucada mesmo.
É? Pessoa meio devagar, né?
É que assim, quem eu acho que poderia fazer é o Serginho que tá lá fora, sabe?
Então, o meu que pode fazer também tá fora, que é o Summer. Mas ele tá voltando, eu acho que dá tempo. Que dia que é?
Hello. 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 Good afternoon. So let's get started. So now we are going to have a talk with Professor Edmilson Freitas. He will talk about Koala and Auditório and PCV.
Yes.
Thank you.
Okay, good afternoon. Sorry. I'm going to talk about the evolution of this project, which is called Koala. It's the project that we are conducting here at USP right now, but it has a history. And the interesting point of this project is the connection between among different sectors, like university, private companies, the government, and the environmental agencies from the state of Sao Paulo and also in a national level. So there's a lot of people working this project, as we expected. The idea, the main objectives of the project started with this program called Auditório. It was a program that was run in other countries like Japan, United States, and some places in Europe and Asia. And it was brought to us by the Ministry of Mines and Energy in collaboration with a company, Toyota. It's an automobile company, a huge one. And the objectives of this project was to provide a technical data survey about air pollution in general, especially gases emitted by vehicles. The main point was to focus on the vehicular emissions. And the idea was to analyze different technologies, engine technology and different types of fuels, and how these technologies and fuels react to give a different standard of air pollution, a different pattern of air pollution in the region. The idea was to also to construct or improve numerical models to analyze the emission data and the concentrations of air pollution using the monitoring network that we had available in Brazil. And one of the focus was over the urban areas, because it's the place that you will find most of the sources, the vehicular sources. And the final objective is to make those results, all the results, models and scenarios available for anyone that wants to study this kind of problem. So it started with the Ministry of Mines and Energy, and it had the collaboration of the Ministry of Environment. There are two agents linked to these two ministries. ANP, which is linked to the energy, and the IBAMA, which is the National Environmental Agency here in Brazil. We have a lot of partners here in Sao Paulo. We have a huge collaboration from CETESB, which always provide us the data from their network. And we have lots of people working here inside the university. We have two laboratories working this project. Master and Lapache are the two main runners of this project. The first phase, which we called Brazilian Auditório, was aimed to investigate the impact of the use of different types of fuels on air quality. And the center of the main focus was centered in Rio de Janeiro and Sao Paulo. The idea was to make some measurements in laboratories, inside laboratories, and use the network available together with air quality models and analyze the use of these different types of fuels and different types of engines, different technologies. So that was the idea. As I said before, the Ministry of Mines and Energy was running the project together with the Ministry of Environment. There is a association, the Automotive National Association here in Brazil, together with Petrobras, with the largest oil company here in Brazil. And we had, at the first phase of the project, the participation of a laboratory that was responsible for taking the measures inside the laboratory, getting the emissions straight from the escape, the exhaust. And we, together with the Technological University of Paraná, we worked in the modeling part of the project. The beginning of the project was based on the information that we have about the fleet. So we started with 2011, and the idea was to create scenarios, the available scenarios for 2020. So we used the different types of vehicles that we have based on the information of the Environment Ministry. And we run lots of experiments based on that fleet. The first phase started with laboratory experiments. We had experiments running light-duty vehicles, motorcycles, and engines to represent the heavy-duty vehicles. So it was like almost 2,000 tests that we ran it around 3 years, more or less, to provide emission factors. That was the main idea. So we run these experiments to provide emission factors for all pollutants that we regulate and some other pollutants that are important in the process of ozone formation or particle formation, which was the main focus. So the idea was to run these experiments to provide emission factors. We did that for light-duty vehicles. We did that for diesel, different types of fuels. Here we have, for example, the most recent fuel, which is S10, mixture with 5% of biodiesel. And at that time, they are starting as the idea of selling the biodiesel with 7% of biofuel. So we tested that before the fuel was put in the market to be sold. And we did the same thing for other types of fuels that were available at that time. In the modeling part of the project, we used 2 models. This model is a model that we started to develop here many years ago, and we're still doing some work on that. But the idea is to provide air quality forecast faster, because especially when we run photochemical reactions, the model spends too much time, and operationally it's not feasible. It was not feasible at that time. Today, it's almost there. And we are also using WorthChem, which lots of students and lots of people here in Brazil and outside and abroad are working with. So the idea was to simulate not only ozone, but particles and other gases. But one of the main focus of our project was on ozone and particles. And for many reasons, but this figure shows the evolution of ozone concentrations in a simulation that was made at that time, 2013. And we can see one interesting feature of ozone, that is the fact that most of the concentrations, the higher concentrations, are found outside the urban areas. And that's something that caused our attention. We see this type of result in every model, air quality model run. And we have some explanations for that, but we wanted to certify that this type of result was correct in the model. So it was one of the motivations. At that time, we made lots of comparisons with observations, and the results are relatively good. This is the result for the operational cycle before we changed the emission factors based on the experiments that we run. And this is a comparison with the same model, but using updated emission inventory. So what we see here is a good relationship. And the most important, we get some, we got lower bias and lower standard deviation for after we improved the emission inventory. So those results were, we have lots other results showing that the model works well. The experiment was very fruitful, and it called the attention of the national agencies, especially those agencies that started the idea many years ago, and they decided to pay attention to our project, actually. In 2012, we elaborated a project which is called Koala, and we made the first submission to the Petrobras and ANP. And well, it was denied the first time, and I think I submitted this proposal at least 12 times or more than that. But as we continued to show the results, they finally got convinced that the project was a good idea. And actually, not only they decide to approve our project, but they created this national program, which is called PCVE. It's a program that has the subject of to analyze those ideas of the auto oil that I showed you before, meaning new technologies for engines, accessories for cars, and new technologies of fuels. So that was the idea of the program. PCVE was approved in 2016, and our project finally was approved in 2017, like more than 5 years after we started the idea. But it's okay. The current program, the national program, has actually 4 different projects. The first one is focused on atmospheric modeling and a mobile laboratory. And also we have another project which is linked to these other 2, focus on the impact of biodiesel, the fraction of biodiesel in the diesel that we have commercially being sold right now. For example, one of the tests that we are making right now, it's about B15, and the next one will be B20, 20% of biodiesel in the diesel. And also, we have recently added to the project, to the program, the bioelectric bus project. This is, I'm not going into details of this project just to get a idea of the project, but it's very interesting project. The idea is to develop a non-plug-in electric bus that runs with almost everything. Probably if you put paper there, they will do something to make the bus work. So it runs with biogas, ethanol, biodiesel, and natural gas, compressed natural gas. So it's a very interesting project inside the program. So after the approval of the program, we started the second phase, which is the Koala project. And the idea is to model the impact of emissions based on different fuels, using surface measurements and all other type of data that we have available to build emission inventories. So that's the idea. So we have 2 lines of action. The first one is air quality cleaning, and the second one is based on a mobile laboratory and field experiments for diagnosis, calibration, and evaluation of the models. So the emissions that we are running right now, that we are working right now, are always based on this model called VANE. Was developed by a former student that was here with us. He's still here. Right now, he's in China. Actually, he's coming back today. Sergio developed this model. And the idea of the model is to give a more detailed information about the emissions. So in this figure, we can see, in this picture, we can see the emissions for light-duty vehicles, for buses, and heavy-duty vehicles. So all these emissions are considering all the routes, the streets, and large highways, everything that is inside the domain. And what the model provides is this type of thing. We have here the emissions, spaces, located emissions for CO, formaldehyde, NOx, PM, and other pollutants that are possible inside the model. We made some scenario simulations. I'm going to show the one that I can't show you. And just this comparison between a real scenario, what we consider the actual situation right now, comparing those results with observations. And we can see that the model does a really good job, actually. There's some issues in these results, but actually the results are not that bad. But we're still working on improving that results, and that's the idea of the project. As it was mentioned before by the other speakers, it's natural to have those kind of things and to see those errors, things like that. So the second part of the project is based on a mobile laboratory, and this is the Lumiar. It's the laboratory that we are using for measuring air pollutants outside the urban areas. And right now, the laboratory is working on a small city called Botucatu. It's in the countryside of the state of Sao Paulo. This is the setup, the station. We have measurements of many gases, particles. We have a partsol here. Tupiniquim is another equipment to provide information on PM2.5 and PM10. We have a Theon here for both measures too. Ozone, NOx, CO, CO2, hydrocarbons, and ethanol, basically, and all the atmospheric variables also. So the idea of the project is to perform some measurements in different sites. We did some experiments here close to Sao Paulo. Right now we are running the experiment in Botucatu, in Unesp. The next site will be Londrina in Paraná. And also we are simultaneously install another laboratory here in Rio de Janeiro. And the last one will be São José dos Campos or Taubaté. We are deciding where we are going to put this next experiment. I'm not giving too many details on that. I'm just going to show one interesting result that we got from the Botucatu measurements. And this is a comparison between the ozone concentrations, the mean diurnal cycle of ozone concentrations. The black line shows the results for Botucatu, which we are measuring right now. And for the same period, we compared with Ibirapuera, which is a station that is close to here. It's located inside a park inside the city of Sao Paulo. And we see that the concentrations are even higher than the ones that we observed here. It's expected, as expected. And that's what we are analyzing right now. There are some explanations for that. It's just showing you what we are going to get there. And that's the idea of the project in general. The Ministry of Mines and Energy is seeking for other groups to be part of the project. So maybe in the next 3 years, we will have more groups working the program. But that's what we have for now. So that's it. Thank you.
Thank you, Professor Edmilson. So I ask Pedro. Professor Pedro is from the University of Campinas.
É muito fácil, não.
Tem como passar?
Será que tem como? Vamos tentar colocar aqui. Ver se ele passa. Vai passar.
Thank you so much. I would like to thank the organizers of this wonderful workshop, Professor Maria de Fatima. We will have a talk about my research project, NOTS, Novel High Resolution Spatial Mapping of Health and Climate Emission from Urban Transportation in the metropolitan region of Sao Paulo. I would like to acknowledge, to give the credit to my colleagues, Professor Miranda from EASE, from the School of Arts and Science, and also Professor Andrade and Professor Kumar, who gave this nice acronym to our project. No? We will try to solve this puzzle, and I think the name is quite good. No, these knots. We will try to solve some problems and some questions. Context, what we know already from the metropolitan region of Sao Paulo. We have a huge universe of vehicles, of inhabitants, 20 million inhabitants. We have high levels of pollutants and greenhouse gases, and we have a big amount of vehicle emissions. This is our context, our background in the project. Some objectives, maybe quite ambitious objects, like trying to understand the activity, the transport activity, in both in passengers and in freight. Try to understand the key performance indicators and environmental impacts of transport in our region. To characterize the movements of our passengers and freight in terms of variations, diurnal variations, but also in terms of vehicle diurnal variations by transport mode, but also by commodity types, how the food, the agriculture bulks are transported in our region. And determine some patterns, spatial and temporal patterns, also related to energy consumption, emissions, or greenhouse gases in this context of mega cities or of big metropolitan regions. Some research questions that we would like to answer with our project. Is it possible to integrate origin-destination mobility surveys to understand the activity in terms of passengers, in terms of freight activity in our city? Can we characterize this mobility to define future policies and how these policies could impact on key performance indicators? Can we integrate these origin and destination surveys? And also some modeling, typical engineering modeling, like stochastic user equilibrium models to reproduce spatial patterns on an hourly basis by vehicle types. Can we complement this this reference inventory with other air quality data sets, as the data sets from the CETESB, environmental company, or measurement from low cost, and also use other databases from the census data, from the Institute of Geography and Statistics. Then it's quite ambitious objectives, and we will try to solve or to answer some of these questions. The scope, we got a source from the FRAPESB as a research regular project, and I will show some of our methodology, some of our basic data, some modeling. We will estimate or present an inventory, vehicle-based inventory, on an hourly basis, on a grid of 500 meters, size of our grid, and we will use this origin and destination survey by transport area zone trips from the mobility survey from the metro company, and together with a huge road network that we have here in the region. We will make our inventories break up by different vehicle types, light duty vehicles and heavy duty vehicles. And we will integrate those emissions with air quality measurements from this test bed and also from low-cost sensors. We will try to replicate the same air quality network as the test bed, but using a different, slight different technology based on low-cost sensors. We based our work on origin and destination passenger and freight sample survey. We have a long tradition of origin and destination survey in Sao Paulo, more than 40, 50 years of long-term data. Then we have a really good database for trying to explain or understand the vehicular activity, the transport activity in our region in terms of freight and in terms of passengers. To have an idea, we have an audit of 100,000 persons and more than 12,000 freight vehicles. This is the sample, the size of our mobility survey in the region. We will make some kind of modeling, analyzing or measuring the production, the distance travel, passengers kilometer travel, the trucks kilometer travel, the logistical reach of our trucks, of our vans in the region, related to the urban form or the activity organization. We will estimate some proxies of energy and CO2 equivalent emission, fuel consumption, and we will use this traditional traffic engineering approach based on a stochastic user equilibrium model, a multimodal or multi-class assignment model based on those delay parameters factors, and dividing or splitting the region in almost 500 centroids, 500 transport area zones. To have an idea of our network, we have about 1,300,000 links. This is the size of our network in Sao Paulo. We will try to integrate new technologies to complement this air quality measurement, this test measurements, using the low-cost sensors. This is the presentation, a map of the distribution of the air quality stations from the CETESB. We have 16 air quality stations in the municipality of Sao Paulo and 12 additional air quality stations in the nearby, within the metropolitan region of Sao Paulo. I divide the region in different colors according to the rodicio, this kind of restrictions that we have for passenger cars in Sao Paulo. This is an enlargement detail of the city center. And we have this 300,000 links. And then this is a quite huge road network. And in some of these air quality, on the nearby of this air quality station, we will replicate with low-cost measurements. This is also one of the objectives of our project. Why the air quality or the low-cost sensors, they are interesting? Because they can give some explanation to what is happening regarding air quality at a relative small cost, and also at a relative quality of the data. And then we found a really interesting solution to enlarge this in the future, this relative small network. And now we are also in the part of the country that we have a relative good air quality network. In some other cities, we have nothing. We have no air quality station in most of the states of the Brazil country. They have they have almost nothing to monitor air quality. And maybe in the future we could extrapolate this experience to other states, to Amazonas, to Acre, to Rondoni. This could also be an output to our project. A solution, they are relative good in terms of cost, but also in terms of data quality, and in terms of spatial coverage. Then for these states, for these cities where we have almost nothing, would be an optimal solution to start having something. This is also a possible output of our project. We are start building those sensors in this kind of boxes, or what they call pods. This sensor, the measurement, they go to a database, and this database is a web access process. This is a quite relative cheap solutions, and we can even put some solar energy and to make the system even more sustainable. We start mounting this air quality sensor. This is part of our the Brazilian creativity. No, here we have a really good technician at the School of Art, who is starting to invent those artifacts, and it's a kind of a telephone, no? And this could be our the outlook of our sensors. They are based on a microcontroller and an Orange P, PC Plus. This is a kind of small and cheap computer to process, to store the data. We start with really cheap sensors, CO2, CO, O3. We bought these sensors with Amazon, with the AliExpress. They are really cheap sensors, also some sensors of temperature and humidity. And we have some previous experience in Sao Paulo from other projects, the Feinstaub Lüneburg project, and the OpenSense. This is a German company who already installed some microcontrollers, some sensors, particulate matter sensors in the city, and also some with temperature and humidity sensors. They are really, in principle, they are really cheap sensors. Similar to the sensors they were presented this morning in Medellin, in Antioquia, in Colombia. This kind of SynGe sensors, and they are quite cheap. Maybe it costs something like $20 or $30 per particle matter sensors. We will compare our measurements with a standard air quality measurements from the Partisol, from the thermoscience. This is the outlook of our sensor. It's a kind of a telephone. This is this inside of this plastic tube. They are installed the temperature and the humidity, and also this box, this particle matter low-cost sensors. And we can compare with some standard and calibrate the result with some standard procedure that we already know in air quality works on. This is from the roof of EASE, from the School of Arts, and we have some rich sources from different fabrics, but also we have in the nearby important highway with a lot of trucks and cars. Some comparison with this OpenSense sensors from this Germany company, comparing with air quality standard data from the TESB. This is here in the nearby of IAG. And here we have different sources. Maybe this is why the data, they are not fitting so well. But in this other air quality station in the nearby of the airport in Congonhas, it looks that the sensors, they are they are working much better. In the future, we will try to establish this correlation, to make this calibration with our own sensors. Due to this restriction, we were thinking about buying a little bit more sophisticated sensors. They are from the AlphaSense. This is a British company. And we have a lot of literature. So I made a good literature review, and all of these papers in many sites in the world, they are using this nice AlphaSense for electrodes of gases, mostly carbon monoxide, nitrogen oxide, nitrogen dioxide, and ozone. And then we decide to improve those cheap air quality sensors, and we will try to replace by this AlphaSense. In Brazil, it's difficult to import everything. No? I almost spend half of my project trying to import the things and trying to solve those bureaucracy constraints. And maybe next week they will finally arrive in Brazil, no? The AlphaSense electrodes, no? from the Great Britain. No? I make a good review of studies using this 4 electrode gas from the AlphaSense. It is a study in Berkeley related to the university. There are some other studies in Boston, Massachusetts, also using this AlphaSense electrodes. We have some studies in Riverside in California. Here also using some kind of infrared CO2 sensor, and those are mobile sensor pods. This is why they install as well a GPS. And we have also some other studies using this AlphaSense in the Netherlands, in Amsterdam. And this is why I decide to replicate those studies here in Sao Paulo based on those AlphaSense sensors. Some of our preliminary results regarding transport, temporal and spatial distribution emissions are related to air quality and also external cost of transportations. We start doing a high resolution modeling of CO2 emissions from these 7 million vehicles. Inventories should match in the future with those low-cost measurements. Then one of the objectives of our project will be to compare those emission inventories with those cheap low-cost sensor measurements. I present some results. This is how the evolution, the growth rates of the air quality in Sao Paulo based on the CETESB air quality measurement. And then in terms of pollution, the situation has improved a lot in terms of CO and NOx, in terms of particle matter, but only in ozone the situation, the air quality is even worse than before. I start doing a modeling of the emissions. This is the high resolution CO2 emissions. We have 500 meters. This is the size of the grid in the map. And we have a 1 hour resolution, time resolution. Those are an estimate of our emissions in terms of kilograms of carbons per hour, and by different time windows during the day, reflecting peak hours, off-peak hours, and evening, afternoon peak hours. We have some temporal distribution of our emissions in terms of passengers, but also in terms of freight vehicles, heavy-duty trucks, compared to some measurements of CO2. We have some temporal distribution of our bus lines. This is a distribution of the routes, the buses in Sao Paulo, and a proxy or an estimation of the bus kilometers driven or travel per hour, by hour. We have also the time distribution related to the trucks but also to other freight vehicles, vans, motorcycles, and small trucks. We have a time distribution by month, but also by time of the day and day of the week. And finally, we end with some inventory, with some CO2 inventory. We would like to have a good estimate of how many tons, CO2 equivalent tons are emitted by our fleet per year. Estimated about 17 million tons equivalent CO2 equivalent per year, from which 73% are related to light-duty vehicles and 27% are related to heavy-duty vehicles. This is a kind of bottom-up approach to estimate our inventory, and we can compare with some previous estimation from top-down estimate from the CETESB, from the state inventory. And I give some estimate in terms of trips per day, but also in terms of millions of tons of CO2 emissions equivalents per year by different vehicle types. Those are urban light-duty vehicles, urban buses, interurban light-duty vehicles, interurban trucks, urban vans, and also in terms of vehicles kilometers traveled. And then we are able to give a first answer to one of our research objectives or our research questions. And the last part of our work is to relate the traffic activities with some socioeconomic factors or socioeconomical effects and space patterns. We have a good distribution of the vehicle kilometer or the passenger kilometers traveled by in the different regions of our metropolitan region or of our mega city. You can see that the people coming from the periphery, they travel more than the people living inside of the city, and that these people living in the surroundings of the city, they are supposed to be more affected to air pollution and also to the external cost or to the consequences to high levels of air pollution. They can even have a good environmental for living. They are living in the hills, in the mountains, with really good conditions of air quality, and they are suffering the high levels of air quality in a more proportion than the rich people living inside of the city. That they don't have to travel a lot because they have their own works in the nearby of their residence, but they are also traveling by private cars, as we have seen from the studies of Professor Prasan or from the studies of Fatima or Veronica, Tiago, to travel in a private car is much more safe than to travel with the public buses or even to walk. And those people living in the surrounding, they are much more affected by the high levels of air pollution. Here is another output of our works. We have a distribution of the main routes of the freight vehicles, traffic flows by different hours of the day. This is showing the peak hour, the morning peak hour, distribution of freight, of loads by different vehicle types. This is for vans, this is for motorcycles, articulated trucks, and small rigid trucks. And we can have an estimation of where the highest concentration of black carbon, for instance, they are much more located, related to this diesel burning of freight vehicles. This is also another of our outputs in the project. And finally, I would like to present a nice work. This is an ongoing work trying to relate the vehicle kilometers travel or the passenger kilometer travel and some data from diseases. I think this, here you can say much better. And the people living in the city center, they are expected to have a lower risk of having some important diseases. This is a relationship between the passenger kilometer travel and the diseases. Then the people living in the periphery, it's the people that they are having lower incomes, and they have to travel longer distance to reach their residence and to commute to their works, and they are also they don't have these safe private vehicles, to use the filters and not to be in order not to be exposed to air quality high levels. And this is a really nice, interesting relationship. This is a contrary what was expected. In the places where we have higher concentration levels, we don't have a higher levels of diseases, because the people, they are not living in the people who are having more diseases, they are living in the periphery. No, they are not living in the places where there are a higher concentration of pollutants. There is a kind of inverse relationship between passenger kilometer travel and diseases, important diseases. And I think this is the end of my presentation. And thanks so much again. And I hope the next year to have a better comparison with air quality measurements using those low-cost sensors that we are still in the phase of producing, in the phase of mounting those devices. I hope to have a better results in this air quality comparison. Thank you so much.
Thank you, Professor Pedro. So I ask Ana. Okay, so Ana Paula is going to present about biogenic sources here in Sao Paulo.
Yes. Hi, I am Ana Paula. I'm doing my PhD here in the IAG with Doutora Fátima de Andrade. And I will talk a little bit about the biogenic sources in Sao Paulo, this part that we didn't talk much so far. So we have, this project is a partnership with DRI and UNLV in the United States, and IAG here, obviously, and is funded by FAPESP and CAPES. So, I think it didn't work. Sorry. Oh, sorry. What's happened? And so we talk a lot about anthropogenic emissions of pollutant and about how much they cause problems, health problems, and also there's several environment concerns about the ecosystem and everything else. So we know that we have several sources like cars and buses and trucks and industry that it's things that we made, like human-made, and they emit pollutants. And they can be primary or secondary, so they can be released as they are, like a particle, or they can be formed in the atmosphere. But we also have the primary natural emissions that are emitted by natural sources. And they can be several different types. So they can be like pollen, can be leaf fragments, bacteria, fungal spores, virus, insects, and also algae. So all these and much more types of microorganisms and other biological parts include these biogenic natural emissions that are called bioaerosols. So they can also be fragments. So they can break in several small pieces because they have like around 1 to 100 micrometer. So they can break and become one particle, become much more than just one. So these are picture of electronic microscope. And if we can see here some pollen, that they are usually larger, one of the largest bioaerosols in the whole structure. And these are fungal spores that we collect here in Sao Paulo. So they have different shapes, different size, different forms and colors. So they can be brown, they can be transparent, they can be a very variable shapes and everything. So the sources of these bioaerosols are several. So they can be emitted by the forest, so they can be emitted in the vegetation. They can have in the leaves, so they fungal and bacteria can grow on leaves and they release in the atmosphere. So we have also the structure like a mushroom in the soil that releases the spores and also emitted, and obviously the soil that when suspended. The ocean also is a source because we have a lot of microorganisms in the ocean, so they are also released in the atmosphere. And we have human sources. Buildings like this one grow molds and also bacteria colonies, so we can have a lot of buildings as a source of these biological particles. And also we are carriers of these bioaerosols because we have bacteria, and you also when we touch something, we are transmitting these bacteria, these other viruses and everything else. So we have a lot of sources. So they can cause several problems like a respiratory disease and several problems like asthma, bronchitis, and especially allergy. They are very problematic in this area, especially pollen that can be a very high allergen, and they have several problems, especially in North Hemisphere, so with these allergies. And they are living organisms, so they can actually get in you and get like a skin allergy or grow or bacteria or everything. So they cause several problems, health problems. They can also be influencing the atmospheric process, so as I told you, they can be brown, they can be transparent, so they can scatter or absorb sunlight, and they also can be cloud condensation on the clay. And they are very important as ice nuclei, because they can, as this picture from Murray, they can be a nuclei, a nice nuclei, in temperatures much warmer than normal inorganic particles. So they can have like some bacteria that can be isonuclei in -1 or -2 degrees Celsius. So it's a warmer temperature than normal particles. And that we don't know exactly how many they are and what kind and what shape and how they influence in the atmosphere. So there is some estimative, but they are very superficial estimative, that 22 to 30% of the total particulate matter have a biological orange. Or one paper that we did here, that we see that a kind of 11%, but this is all statistical analysis because we have so many kinds and so many variables involved in that, so it's estimative. So we are trying to understand how much of the PM10 is bioaerosol in Sao Paulo metropolitan area. So we collected with several equipment. So we collected with high-vol, mini-vol, Burkhardt. With high-vol, it's a high volume sampler. We collected with quartz filter and did all this analysis. Element, ions, organic carbon, elemental carbon, carbohydrates, organic acid, total protein. And with the mini-vol, we collected with other, it's a low volume sampler. So we have the mass of the PM10 and some elements too. And with Burkhardt, it's a device that we collect samples and analyze after in the microscope. So we count and identify the fungal spores and pollen present in the atmosphere. So we use all these. So and the first one, the high-vol, we analyze in DRR and UNLV in United States. So we have a lot of data, a lot of information with these filters, and we will try to use these information to separate the sources of PM10 and try to see how much of these is biological and how much is not. So to show here, I did a fast description analysis, just a temporal analysis to try to understand the data. So we also did a PMF and PCA to try to separate the sources of the PM10 and try to see if you can find a biological source. And use conditional bivariate polar plots to help to separate the sources and see how the wind direction and wind speed influence in these sources. So to do that, we have to do some, we have to calculate the uncertainties of the analysis. So it's configured, I'm sorry. We have to calculate the uncertainty, so you have to use precision and analytical uncertainty, and then total uncertainty considering the equipment or uncertainty too. So we collected here the samples in this building, in the other building, but in AG. And we have 69 samples at total analyzed. So we have May to November days around it, and 24-hour samples, and also March and April of 2018. Here I just put in the percentage just to see the variability during the seasons. So it's not the concentration, it's just the variability. So you can see that the PM10, that is the mass, PM10, and some ions like sulfate, ammonia, and nitrate. They have higher concentration in winter, as we know that this happened. And we have also the organic elemental carbon that have also high concentration in autumn and autumn. But this picture is interesting to see the difference between this arabitol, mannitol, and glucose. These two, arabitol and mannitol, are very used as biomarkers of fungal spores. So they can, they are present in the cell wall of the fungal spores. So if you find these compounds in the atmosphere, it means that there is some spores in there. So we can see that they are opposite. They have higher concentration in autumn and lower concentration in winter. And we will see why. So just see the difference between them. So they behave completely different from these other compounds. So Levoglucosan and mannose are also some biomass burning markers, tracers. So they also have a high concentration. Ozone, which is related with organic and elemental carbon. And these are organic acids that are related with secondary organic aerosol, and this one with exhaust engineer, so we've related with cars. So we can see that they also have high concentration in winter or autumn of 2017. So this is just the same thing, it's just the variability. It's just for us to see the precipitation that is more important here. We can see that there is higher precipitation, rain more in autumn of 2018 and spring. That means that we have lower concentration of pollutants, white depositions, and also because of the other factors. But we have a lot of fungal spores in this period because they need water, so they need humidity, they need some kind of spores need the actually drop of water so they can be released in the atmosphere. That's why we can see that they behave completely different from the other pollutants. So here I just put the time series and selected 3 days with higher concentration of PM10, so we can understand these high events, what are influence them. So we have we can see that actually the ammonia and nitrate and sulfate did not have higher concentration in the same periods that the PM10 mass in general. So they have the same month with higher concentration. You can see that September here has higher concentration as here, but these peaks are not related to that, but are related with organic carbon and elemental carbon. And also with levoglucosan in all days, but especially in the first day. So, which means that this period we have high biomass burning, and we get a high peak of PM10 because of that. The last day we have the last high day, and we have fermate, that is organic acid, and I relate with secondary organic aerosol, and we also find high concentration in this period, relating that the source it's higher in this period. So I put also mannitol here, just that's one of the traces for fungal spores, and to compare to see how much they actually doesn't work as the other pollutants and other elements inside the PM10. So they actually behave quite different. And these are the, also it's configured a little bit. This is also all the traces that we have for biosols for now. So we have mannitol and arbitol that are the biomarkers, as I explained. And this is total spores, is the amount of spores that we counted in the microscope. So it's the number of spores per cubic meter. So we can see that they both have the same behavior, and they correlated quite well with 0.5, but this is well because total spore count is very very difficult. It's a manual counting. So we have a lot of error involved in this. So this explains why the 0.5 is considered high correlation. And this is total water-soluble protein. So we find that they don't seem to relate it very well with other tracers or the total spores. But this is understandable because this is all protein. So everything that is biological in the atmosphere that have protein it's in here. So we have pollen, we have bacteria, we have fungal spores, we have algae, we have a lot of things. So the fungal spores behave like this, but pollen doesn't. So we have a preliminary results for pollen. So we can see that pollen doesn't behave like fungal spores. They have high concentration in spring, that's September, October, and November. So they are very different. And here we have high concentration in October, but we are not showing here, but we have. So, and putting together pollen, spores, and other things, we can see that this total protein will make sense. So Bauer did a conversion factor to convert the mass of arabitol and mannitol to number of spores and then to mass of PM10 and organic carbon. So I use this conversion factor, and here we have in these 6 night samples that we are talking about, 3% of the PM10 mass it's from fungal spores, and 7% from organic carbon. And it's similar to the other paper that we published about that was in 2015, that was 2 and 8%. This seems very low comparing with other things from PM10, but it's not, because we have to consider that this is just fungal spores. We have lots of other bioaerosols there too. So we have to consider that, to consider all the bioaerosols mass. And total protein, because they are just molecules, you know, so we have a lot of things besides the protein inside a pollen or a fungal spore, so they contribute very little to PM10. So we did a PMF to try to separate these sources, and we find 6 sources, but they are a little bit mixed. But we have first source like a vehicular emission and a secondary inorganic aerosol, because there is contribution of ammonia and nitrate. And second factor, we find organic acids along with some crucial species, so probably also a vehicular emission and pavement suspension. And the third factor is biomass. So as you see, biomass burning can contribute to PM10, and it's significant. The fourth factor that is more interesting factor is the vehicular emission, and the biomarkers is in that factor. So we cannot separate them yet, but we just use arabitol and mannitol. We will try to do another with total protein and with pollen and spores. So maybe we can get a more separate factor in there. And we have marine aerosol and crucial species, like the soy, it's a normal source. So the contribution in the mass means most of them is vehicular. These two, it's vehicular. And the last one, it's soil, so it's what we expected to see. So we used this technique, CBPF, to try to see if we could separate better, or at least understand better each source. So we can see where they are coming from, so we know kind of what source they really are. So we see that here the first one is the vehicular emission and secondary inorganic aerosol. They have contribution in the southeast, but the local wind, the wind speed, don't contribute a lot. So low wind speed, they have higher concentration, so probably a local source. And also organic acids, we have high wind speed in southeast. This southeast, we have industry area, so maybe there is coming something from there. And also biomass burning coming from the northeast. We know that we have some sugarcane burning in this area, so which makes sense. This is vehicular and biogenic source that they came also from northeast. Marine aerosol came from the east and southeast, and the last one is soil that have also low wind speed, so probably here. So this is the arabitol and mannitol, the tracers, and we see that they have related with high wind speed and from the northeast area. So that factor that we find here, that they are here, it makes sense. They are actually here, so they came from this area. And a multi-regression with total protein just to see if they related with some of the sources. And we see that they related with source 1, 2, but especially with 4, that we find the biomarkers for fungal spores. So probably when we do all this data to, again, we will find more interesting things. It's just that. Thank you.
Thank you, Ana Paula. So I ask Ashish.
Can I put it? Third one.
Yes. So you can use this. Okay, let's take and you can use this to So thank you, Ashish. Ashish is going to talk about exposure to implant babies. Yeah.
Yeah. Hi, good evening, everyone. This is Ashish, and I'm a PhD student at Global Center of Clean Air Research under Professor Prashant Kumar. And I will be talking about some of the field work we did. So these are some of the snapshots of my results. So it doesn't necessarily include almost everything I have done. So while almost like we have been listening to previous speakers, everyone has discussed that air pollution is such a big concern to public health. But this study is mainly about young children, air pollution exposure, mitigation, and control. So sort of quantifying how much excessive exposure they get when babies are transported in prams in roadside environments. So this project is funded by UK government, EPSRC, Engineering Sciences and Physical Research Council, and partly by an industrial partner, Brezzi Limited. So these are some of the, this is how I will proceed. I'll start with motivation and background for this research, then broadly talking about aims and objectives, some of the literature review findings, methodology, and then results and conclusions. So the importance of air pollution cannot be overemphasized, as we know that air pollution is such a big liability. But again, reiterating some of those facts because it keeps us sort of motivating and to keep ourselves focused on this issue. So from the statistics of UNICEF 2017, almost 6.5 million people die annually due to poor air quality, and which then makes air pollution as greatest threat to human health in UK, and it's almost fourth greatest threat to the public health after cancer, heart disease, and obesity. And most importantly, young children, especially babies in prams, which are being transported by parents when they drop off their elder kids to schools and pick up from schools. So these are the most affected ones and most vulnerable subjects of study, which I found little bit sort of neglected so far, which was revealed after literature review. Only 4 studies we found so far. So that puts us at some of the sort of challenges, and as well as at the cutting edge of this research area. So almost 17 million babies are living in severely affected areas where air pollution limits are not being followed or not being met. And from the more recent 2018 UNICEF analysis, almost 1 out of 3 babies growing in the UK with almost very high level of particulate matter, which are not following any sort of World Health Organization limits or other pollution limits. So almost 270,000 babies under the age of 1 in the UK are living with such unsafe levels of particulate matter. And when we sort of expand this age bracket to the age of 0 to 5 years old, then we find that almost 1.6 million babies under the age of 5 are growing in UK with unsafe levels of particulate matter. So this is almost 1/3 of all the 0 to 5 year olds in the UK. So this is some result from one of our paper published in Environmental International, which is quite a high impact journal. So this is a typical setting of roadside environment when babies are being sort of transported like this, and we see the vehicle flow on the roads. So we consider a typical setting where the wind is blowing from the leeward side towards the windward side, and there is recirculating air which then sort of pushes all these pollutants towards the baby breathing area. And baby breathing area is almost located in the same height, which is almost 1 to 2 meters from the ground level where vehicle tailpipe is located. So this sort of makes them very vulnerable to such exposures. And this is also the level of incremental exposure of babies compared to adults. And also, like, this is also justified by some of the other previous studies on particle number concentrations, out of which some of the studies are from our group only. So they looked into the particle number concentration, vertical and horizontal variation, and they found that concentrations usually follows this exponential curve, and they decline exponentially. So this again puts the babies into a further sort of vulnerable area, that they are sort of exposed to higher concentrations compared to adults, because adults are breathing at relatively higher height, which is normally 1.7 meters from the ground level, whereas babies are breathing at almost 0.7 to 0.85 meters from the ground level. So this is again sort of reiterating some of the health impacts of all these criteria pollutants. So if we consider across all age groups, then as some of the speakers previously said, that elderly and young children are the most affected and are the most vulnerable. So there are a lot of studies, epidemiological studies, which have found correlations between concentrations of all these criteria pollutants, including PM2.5, PM10, NOx, and the occurrences of asthma and deterioration of asthma for already existing patients, and increased number of hospital visits, and so on. So, and most importantly, black carbon is also very important sort of pollutant, and a lot of studies have been done for understanding the impact of black carbon exposure on the cognitive abilities, performance of young children. It lowers their lung function, it affects their cognitive behavior, it affects their IQ levels, it affects their rational thinking. So these sort of studies, a lot of studies have been summarized in our paper, which is already published. So most of us are often confused that so many pollutants, and all of these we cannot certainly control at once. And one of our senior presenter, Professor John, also said that when we consider about mitigation and control of all these pollutants, then we should also take care and consider about co-benefits of some of these pollutants, and also the consequences. If you try to fix one problem, then you end up with other problem, and other concentrations are increased. So I think, that ultrafine particles are very important pollutants on the right side. So these are really very fine particles, and when we talk about one of the important characteristics of these particles is toxicity, as Anna and others also presented, that toxicity is really important when it comes to really understand these properties. And finally, these particles are greater is their toxicity, greater is their surface area. So these ultrafine particles have higher pulmonary deposition efficiency, and they have very unique chemical composition, and they causes all these problems which we have discussed. And more importantly, young children and in-prem babies are very vulnerable to these pollutants, because they have very higher breathing rates compared to the adults. So the breathing rate of in-prem babies is almost double compared to the adult breathing rate, and this when compared to their the area and size of their body and per unit body weight. So this puts them into a more vulnerable position, that they are more exposed to such pollutants. And other reasons are that they have developing bodies, they have developing lungs and systems, and also they have permeable cell membrane linings, which then makes them further vulnerable in terms of health impacts of all these pollutants which they inhale. So the overall goal I am sort of iterating here, the overall idea is to really critically assess and compare the exposure levels of babies in prams and how much additional exposure they get compared to the adults. And then we are trying to develop some sort of conceptual framework with recommendations for improving their exposure levels. And also there are further objectives to understand the physicochemical properties of these pollutants roadside through SAM analysis, and what are the characteristics of those pollutants, and then how those characteristics are then related to the further more bigger, broader picture of health impacts of all these physicochemical properties of these pollutants. So as I said, like there were only 4 studies published in pram babies or in trailers at this baby heights. So there was no existing sort of classification method of classifying babies or baby transporting systems. So we sort of classified them based on 3-wheeler and 4-wheeler and based on the baby sitting heights and how far they are sitting from the ground level and how far they are located from the pollution emitting source, which are vehicles from the roadside environment. So some of these we utilize for conducting an extensive field campaign of almost 50 plus hours, and that was then accompanied combined with 35 hours of co-location field data. So almost 80 to 90 hours of field data we are talking about here, and that we have been analyzing and really trying to sort of understand the variabilities in exposure of in-pram babies when they are transported in different sort of prams. So this is a pram facing where the baby is facing parent is pushing the pram this way. And then we did a lot of measurements in this sort of pram. We did a lot of measurements in this sort of pram, which is with this one, which is facing roadside, where babies are directly exposed to all these vehicles when they are being transported on the roadsides. And another important pram was this double pram, where babies are sitting at the lower height and at the double height. So we also try to really understand the differences in the exposure with the differences in sitting heights. And so 2 more most important things we could find that which might or which affect their exposure levels. One is the width of these prams. So the width of these prams is about like how much far they are located from the roadside. So this does have an impact, as some of the speakers did speak about, like the distance from the pollution source is a major determinant of the exposure of the subjects. And other important factor is this breathing height. So as we discussed previously, that there's exponential variation of this concentration. So babies are breathing within 1 meter from the ground level. So this has a very significant impact on their exposure. So these are 4 studies, and out of which 1 is ours. So so these are the comparisons, and different studies did find that babies are exposed to higher exposure. These are babies' exposure. On y-axis we have PM2.5 and ultrafine particle and NO2 concentrations. And in green bars, this represents the breathing height for babies and adults. And in most of the studies, the differential exposure of babies was almost 5 to almost 60% higher than adults. And so there was huge differences in different studies as well. But babies were exposed to higher concentration than adults. This was a sort of a summary of reviewing all these studies. So 2 or 3 important factors we did identifying from this literature review, from this exercise, that these are the most important factors which affect the exposure of these babies. One is, like as we saw from that plot, the exponential decay of the concentration profile, that these concentrations decay exponentially. So if you are breathing at a lower height, you are supposed to be exposed to higher concentrations. And also the proximity with the roadways. So the width of the pram that defines like how far they are located from this vehicles traveling on the road. And also the location of the vehicle tailpipe close to the passenger side, as we see from some of the literature review that they recommend in order to mitigate the exposure from vehicle tailpipes. Some of the vehicle tailpipes are located vertical. So when they're located vertically, then it means that the dispersal of pollutants is vertically, and which is much at greater distance than from the subject. So it then helps in sort of mitigating exposure of the commuters or the babies. and also the duration of how much duration these babies when transported on the roadside, then how much duration do they spend on traffic intersections, 3-way traffic intersections or 4-way traffic intersection, and this does have a lot of impact in terms of how much dose they are getting in the dose response calculation, which we have not yet done, we are working on it. So here we were trying to sort of model the flow and dispersion of pollutants around prams. So this is just to set the context if someone wants to proceed ahead with this analysis. So this is a graphical representation like how the traffic flows on the road, and there's a trail of there is a sequence of vehicles passing by, which then leaves a trail of pollutants, and these pollutants through the wind speed through the flow of wind, then they transmit all these pollutants to the baby breathing area. So when we talk about babies exposure in roadside environment, then the most closest scale to model this study is vehicle wake scale. And vehicle wake scale, they are modeling experts here. I'm not modeling expert, but we'll try to sort of throw some sort of scratch the surface. So there are two wake scales, near wake and vehicle far wake. And in the near wake, it is mainly dominated by vehicle produced turbulence, which is because of this turbulence. Whereas in the far wake region, it is mainly predominated by wind produced turbulence. So since babies are located in this area being transported, so they are more affected in the vehicle far wake scale. And in this region, this wind produced turbulence is dominant, and there are no visible flow structures around this area, and there's lesser turbulence compared to the vehicle produced turbulence. And this is again the sort of like the flow of pollutants, how the pollutants flow across the baby pram. So this is just scratching of the surface to just give a visual of how babies are exposed to the pollutants. And this is our route which starts from our GK lab, Global Center of Clean Air Research, and the route was maximized to pass through maximum number of traffic intersections and bus stops. These two bus stops are within the university campus, so they keep on coming after every 10 minutes, so there's a lot of concentrations within the campus as well. And then it passes through 3 traffic lights, where if you transport your babies, then almost 3 to 4 minutes you stop at those traffic lights, which then affect your exposure levels of these babies. So this is single pram facing parent. In this, we did a lot of measurements. This is a single pram facing roadside. Here, there is this. We also did a lot of measurements with this clean air sort of device. This is manufactured by our industrial partner. So this sort of sucks dirty plume and then pushes clean air and creates a sort of clean air area within baby breathing area. So we tested this device, but we didn't include some of these scenarios. We are working on some of the analysis. There was some sort of hiccups with the device because the filter was old and it couldn't be changed. So we are still working on it. And this is the double pram. So 2 sets of instruments are placed, one at the bottom height, one at the double height, at the top height, to understand the variabilities in the exposure. And these are the instruments, some of which also some other previous researchers have also used, Veronica and others have also used. So first is GRIM. This is in the particle size range 0.25 to 32 micrometer, and P-TRAC for ultrafine particles, Q-TRAC for carbon monoxide, microearth for BC, and then we did also Joule SAM equipped instrument with one of the state-of-the-art lab at University of Surrey to understand the physicochemical properties of these pollutants. So there were different time resolution from 6 seconds to 10 seconds, and they were all then averaged to 1 minute, and then we sort of compared. So these were different scenarios. Almost there were 8 scenarios, out of which some of these were neglected because of the problems in the device. This one with the clean air device. So almost 89 single runs and 45 hours of campaign plus 35 hours of additional data of co-location. These are the concentration profile for like how much concentration they are exposed to. So at some of the places, the concentrations are higher near the traffic intersection, but while at other places, it's not essentially at the traffic intersection, but because of the pollution being sort of, these pollutants being sort of accumulated, and then we see these sort of dark red areas, which means higher concentration. This could be the reason, like it also has some sort of street canyon effect. I don't exactly know whether it's a street canyon or not, but there is a sort of canyon effect, like on both sides there are buildings and then these pollutants which don't get dispersal, which don't get dispersed easily. So dispersion is sort of prohibited because of all these buildings. So that's why these might be showing some sort of dark, sort of these high concentrations. This is in PREM, this is in backpack. So this is the time series plot of PM2.5 concentrations. These peaks essentially refer to the traffic intersections, and so these trends were, a lot of time series plots I do have, but I am only giving some snapshot of the results, not presenting all the results here. So babies in PREMs at PREM height in sky blue color are definitely exposed to higher concentrations compared to this orange color time series plot, which is concentration at adult height. So the similar sort of results of time series trends we found for other pollutants as well. But this is just for PM2.5. We have for PM10, PM1, PM2.5 to 10, and NOx. So this is again the comparison of exposure in PREM. There are two different sort of PREMs, facing parent and facing roadside. So in this yellow color, this is exposure of in-PREM babies, and this in green shade, this is adult height. So these are two types of PREMs, PREM 1 and PREM 2, and morning and afternoon. And for these, all these pollutants, PM1 to PM10. So the trends does reflect and again sort of validate the fact that babies are exposed to higher concentration in all these plots. And of course, there was a lot of standard deviation and huge variability in the data as well, because air pollution data doesn't necessarily follows the normal distribution. It is sometimes log normal and sometimes exponential, so we can't really sort of say, but there was a lot of standard deviation and huge variability in the data at different time steps of the different runs. And this is PNC concentration trend, which is again consistent with the fact that babies are exposed to higher concentration compared to the adult height. So that's it. And so from the literature review, we summarize that babies' exposure to traffic emissions affects their frontal lobe, cognitive thinking, brain development, and all these sort of health impacts we discussed. And classification of baby PREMs revealed that the distance of the height of 1 meter above the ground level is really critical in terms of assessing and quantifying and understanding the exposure of in-PREM babies. And from the literature review, babies were getting almost 60% higher exposure than adults, but our analysis then find out something else, but almost in the same lines. So fine particle exposure at in-PREM height was almost 44% higher, and for BC and coarse particles showed mixed trends. The trends were not always consistent for BC and coarse particles. And so most importantly, like these meteorological factors does had a lot of impact on these concentrations, mainly wind speed and wind direction and built up features along these roadside environment, which then affect the dilution, dispersion, and mixing of all these pollutants to which babies are exposed to. And we also summarize like some of the passive control strategies for mitigation might include face mask, which is like public protection equipment. They are available in different sort of styles, and we are also testing face masks for their percentage penetration and percentage efficiency of removal of all these pollutants. This is in the pipeline, and we are working on it. And so fine particle concentration exposure was substantially higher, and concentration exposures were affected by the type of PREM, baby sitting height in different sort of PREMs, and these built up features and meteorological conditions. And a lot of runs we also did with the PREM covers, but that again, like the results are not included here. And the PREM covers were mainly effective at mitigating concentration of fine particles, while they were not so effective for coarse particle and BC concentration exposures. So that's it. And this is our team, and a lot of many volunteers contributed to these field campaigns. There were almost 6 to 8 volunteers, including some from Sao Paulo, from Brazil, Janena, she's in different uni, and G-Care volunteers, and this is our industrial partner based in London. And it was quite motivating to see that our study first paper in Environmental International was picked up by almost 30+ media houses internationally. It is BBC, UK Daily Mail, Huffington Post, and Daily Mail, Telegraph, and a lot of media in India, Brazil, and Canada, and everyone almost talking about it. So it was sort of motivation. When we face challenges, then it really motivates us to really drive us, because there are not so many studies, so there are challenges as well. So thank you, that's it.
Thank you, Ashish. So we have time. So I asked the speaker to come here. We have some questions to. Professor Edmilson, Pedro, Ashish, and Ana Paula. Questions? Sorry.
I'm Yang Zhang from NC State. Thank you all for nice presentation. My question is for Professor Edmilson. And you showed the ozone forecasting or modeling and the diurnal variation, right? And in comparison with observation. And it looks like ozone concentrations are over-predicted during the daytime. Then during the nighttime, we see a spores peak there. So do you have any explanation for over-prediction of ozone during the daytime and for the artificial peak during the nighttime?
The over-prediction, it's mainly because actually we don't have all the sources, the correct sources of the precursors. We are considering only vehicular emissions, and the other sources in our results are not being considered. So part of the error is due to that lack of representation of the precursors of that are important. Another explanation is the fact that well, it's something that we didn't analyze yet, but actually atmospheric conditions need to be accurately represented, and it's something that it's not perfect yet. I mean perfect, it's far away from the reality. Worth model over urban areas tend to overestimate the wind speed, and this causes some errors too. So there are many reasons for this over prediction. The nocturnal concentrations in the model also will depend on this atmospheric condition, because as we see in most of the observations, sometimes, and it's very common, it's being constantly observed in the network, in the CETESB network, and other experiments that we made. It's common to have these secondary ozone peaks. And the model has some difficulty to represent those concentrations. One reason is because the domain of the simulations is not large enough to represent the main feature that causes those concentrations. Those concentrations are caused by transport, horizontal or vertical, and sometimes the ozone concentrations goes away from the sources, and they are brought to the same place again by the circulation, the local circulation. If the circulation is not well represented in the domain of the model, it's hard to represent those kind of features. Also, the NOx concentrations maybe need some adjustment. When we compare NOx with the observations, they are a little bit different. So if we have higher NOx concentrations in the model, during the night the concentrations of ozone just go down. So maybe something that we need to study more detail.
Well, thank you for your explanation regarding the daytime overprediction for ozone. Typically, missing additional sources could explain underprediction instead of overprediction. So in your case, it could be inaccuracy in the emissions, or have you taken a look at meteorological model performance? And that's one question. Regarding the nighttime spurs peak in ozone, and there are two major reasons we found out over US. One is the under prediction for NOx titration. So you want to take a look at how the model predict NO2 to see whether they help explain this peak. Then the other reason is the underestimation in the nocturnal mixing, and you can take a look at the floor value for KZZ. And in early version of Wolfram, and they are not well represented. And even the value are there, but it's probably more applicable over North American atmospheric condition. So it needs to be adjusted for application over South American here. So those are the two major reasons we identify when we adjust either the KZZ value or adjust the NOx emission, getting better nocturnal NOx mixing ratio. We see disappearance of those spirals, artificial peak during the nighttime.
Okay, thank you.
So, okay, I will thank all speakers. I invite all of you to a coffee break, yeah, so we can make some questions and continue this discussion with the speakers, yeah, okay?
Okay.
Thank you, thank you.
Hello. Now we are going to the last section of the day. This last section is dedicated to the new project that we are conducting now. And Professor Eduardo Landulfi is going to present. He's going to start the presentation of the project, and then we have other colleagues that will present some specific parts of the project.
Não sei. Você prefiro esse aqui.
Você pode pôr isso no bolso.
Esse aqui eu estou sem bolso.
E esse aqui?
É aqui. Já está aqui, está tudo certinho. Entrou um time view. I cannot move my arm, otherwise it starts. Okay. So good afternoon, everybody. So this is the, let's say, the last session of the day. This is the new project that Fatima is coordinating with them. Then we're going to show all the list of collaborators. And actually, this project, well, as you saw, many of us have been looking to aerosols mostly, right? But then you know that greenhouse gases, especially produced in cities, in mega cities, is also a big issue nowadays. And given that we actually, Fatima made this project, we put everybody together to FAPESP, which is a thematical project. And then we're going to show the startup. Actually, the project was approved at the beginning of this year. So we are in the process of acquiring all the equipment, deciding some strategies. So we're just showing you like more or less what was our kickoff meeting about like 3 months ago. Okay. So the cities now, this project which you can get from this site, the 40 cities, are cities that concentrate a fairly amount of people, and of course they also driven a lot of energy consumption, and of course pollution emissions, and of course greenhouse emission, right? So this is like, it's not really a project, but this is a consortia of people thinking about how to tackle all these problems that the cities, especially the mega cities that we see here in South America, for example, you have North America, Africa, and so on. So then Sao Paulo is one of them. So the project that was conceived, we had development of an integrated framework to estimate the source and sinks of greenhouse gases and surface production in the metropolitan region of Sao Paulo in neighborhood. So the strategy would be like making continuous measurements of surface fluxes and also get the vertical columns of those measurements. So the principal gases would be CO2 and methane. And of course, that would be integrated with models, chemistry transport models, and of course, assessment with air quality. So Fatima managed to put a lot of collaborators together, and you can see here the list and all the institutions that are involved. And this project is part of also a project called Mega Cities, which is conducted by JPL in the United States. Okay, and you have many collaborators, and of course, as the project develops, we should have like many students involved. So the framework of the project, so you have the model part, the emission inventory, and of course, and then the observations, okay, and then the satellites also to monitor everything. And so we have many, let's say, modules for example, the particles will be still like being monitored with remote sensing, in situ surface, and of course the gas phase. As I said, CO2 maintained, of course ozone, and of course water vapor can be also put into this budget. And seen from the surface, and also from satellite and measurements from the ground. Okay. So this is like the diagram of the emissions that we consider in the modeling that I think you had the chance to discuss this today with Edmilson. And of course, the area of the mega city that we're going to use here is more or less like 100 by 40 square kilometers. And so it's a large, fairly amount of area. And of course, we have a very topography that's also very challenging. Okay, so to give you a flavor what we are now, we have like USP here, where we are now. So USP Leste, then this would be, let's say, potential sites for this approach, which involves, as I was said, the modeling, the satellite observations, surface measurements of concentration, and also fluxes measurements, and ultimately also FTIR to get the column integrative of CO2 and so on. Oh, sorry. Okay, so in the phase that we are now, as I said, that we are acquiring the systems, and also we are now deciding what would be the next sites to put these measurements to get the fluxes. And actually, yesterday we had a very good discussion about how to deploy those systems, because of course, you know, you have always, budget is always a limit. We should have like 4 sites. We have 1 site already running at Pico do Jaraguá, but then we have to decide other sites for measuring both fluxes and also the concentration. And one good aspect of that, because you have to see that some sources from CO2 might not be the same sources for methane and so on. So that will be, it's the first challenge, but we believe that the first equipment should be arriving in 2 to 3 months, maybe less than that. Okay, and of course, we know that not only looking at Sao Paulo is not only the challenge, because you know that the whole state of Sao Paulo also has other, let's say, hotspots for methane and CO2 and so on, but this should be like saved for the future after 2 or 3 years of the project. So I think that's all from myself. Thank you. Regina? Yeah.
Fechou? Acho que tava. Ou esse aqui, assim.
Esse aqui.
Deixa eu fazer o negócio que ele pediu aqui.
Opção de setas.
Como é que é? Ixi.
A opção de seta, mas está funcionando. Aqui.
Tá?
Tá. Só apertar.
Visível.
Isso.
Pronto, é isso que ele falou para fazer.
Okay.
So very briefly, I'll talk about surface measurements. So as Eduardo said, the project has a lot of goals, a lot of objectives, different objects. And my contribution will be with surface measurements. Oops. So focus will be greenhouse gases and short-lived climate pollutants, just to remember. Not working. Oh yes, now. How de cima? Yes, okay. So black carbon and methane and ozone. So we will make some measurements during the project in different places, and some of them are already working. So, for example, in Botucatu, and here in Sao Paulo, here at IAG, and also Dr. Arnaldo Avenues, Public Health faculty, and since the beginning of the year. And now we are starting at USP Leste also. So, because Sao Paulo has Sao Paulo metropolitan area, we have problems with ozone and particles. And for example, 78% of NOx, 97% of CO, and 82% of volatile organic compounds are emitted by vehicle fleet. And nitrogen compounds are associated to diesel combustion, and fine particles emitted by vehicle fleet. And particles are composed mostly by carbonaceous aerosols. And Ana Paula gave you some PMF results about aerosols. And we have another studies in other parts of Sao Paulo also. And these are the objectives of the project, as Eduardo said. So we have field campaigns. And here, our instruments. So we have trailers. We have some in situ measurements. This is for black carbon. This is a photometer, cascade impactor, and this is a here. He is a particle instrument, partisol also. Okay, and the idea is to use different techniques, so complementary techniques to evaluate. For example, for mass concentration, we have partisol and cascade impactor. And for organic compounds, we have some analysis like gas chromatography. And for elemental carbon, we have some monitors like a MAP and ietalometer and sunset technique. And for inorganic compounds, we have ion chromatography, X-ray fluorescence. And also we have reflectance technique for black carbon, and CAM for shape and size distributions, and also magnetic properties for using different technique. We are learning about that. And plumb isotopes in geochronology laboratory, and LIDAR from IPEM, and gaseous measurements with some different instruments. And now, as Eduardo said, sites where the measurements will be carried out are being studied. And now Newton will talk about satellite measurements and optical properties. Yes? Okay. Essa aqui é sua, não, né?
Deixa eu pego aí. Good evening. Actually, I'm in the working group 3, which will focus on aerosol optical property and radiative effects. What I'm going to show you is an overview about aerosol optical property in Sao Paulo, which we know. Okay. We have almost 20 years of monitoring of aerosol column optical property here, using Aeronet CML and photometers, and multi-filter spectral radiometer. Basically, Aeronet station provides us with optical depth, information about absorption, size parameters. MFR provides us with spectral optical depth, size parameters. And I'll show you about what we are learning using this instrument. This is just an information about seasonal variability of aerosol optical depth in Sao Paulo. This is our instantaneous aerosol optical depth for many years. So we can see that there is a strong seasonality where the highest aerosol optical depth are observed during September and October. But also we can see few events of local polluted aerosol. I'm saying local polluted events because these high events of aerosol optical depth are mostly related to smoke transport from biomass burning regions. So this is a characterization that we were able to learn using these instruments. And here we can see the angstrom exponent, which provides us an idea about size distribution of the aerosol. As you can see that most of the value are above 1.0. That means that there is a fine particle dominance here in Sao Paulo. So this is information that we have already from these instruments. This plot shows single scattering albedo, which provide absorption information, against size parameter, which is asymmetry parameter, including almost all stations, ionization stations that are operating here in South America. Northern Chile data, Suriname data, Amazonia, northeast of Amazonia, green, here south of Amazonia, black. And the special thing about Sao Paulo is that, which is in this triangle, the red triangle, is that Sao Paulo has the largest variability in single scattering albedo. And it has the highest absorptions aerosol here. That's have to do with the different type of aerosol that affect Sao Paulo atmosphere. And usually this high single scattering albedo, which means that it's not a highly absorbing aerosol, are usually observed when we have this transport of biomass burning over the city. When there is no transport above the city, we are able to observe low single scattering albedo, which means high absorbing aerosols. So we know that this highly absorbing aerosols are related to particles from the city, and when the single scattering albedo increase, usually it's related to smoke transport, which can be related with the high value of aerosol optical depth. We did some tests in terms of heating height profiles, considering both scenario. He is just using just a vertical profile, considering only local aerosol in the boundary layer. In this case, we have local aerosol in the boundary layer and smoke transport aerosol above the boundary layer, since we know that most of these transports occur at 2 and 2.5 kilometers above the surface. So what we can see here is that there is a lot of information here. In black color is without aerosol effect. Blue is early in the morning. Red means at noon. And we have different kind of aerosol: low absorbing aerosol, moderate absorbing aerosol, highly absorbing aerosol. And of course, we can see that there is an important impact of aerosol on the heating rate, which depends on the diurnal cycle. And here we can see that when you have this smoke transport, the impact early in the morning is important. It's not the case for local aerosol. And when we at noon, the impact at boundary layer, in the boundary layers, it's almost the same that we see at aloft. These are effects that we are modeling using only radiative transfer models. This is not yet evaluated, the impact of these effects on meteorological scenarios. So this is something that we will be able to do in the context of metroclimate. This is just to give a perspective of aerosol direct radiative effect compared with cloud radiative effect here in Sao Paulo. Of course, during the wet season, the cloud radiative effect in terms of reduction of solar radiation at the surface is dominant. But we can see that during the winter and the dry season, there is the aerosol radiative effect is comparable with cloud radiative effect. Mainly here when we have these smoke transport events. Aerosol indirect effect is something that it's still to be evaluated for Sao Paulo. We know few about aerosol indirect effects in Sao Paulo. So this is an aspect that I think we will be able to work during this project. This is a study that we did with Judith from Federal University of Rio Grande do Norte, which is try to understand the correlation between our aerosological depth variability above Sao Paulo with other regions around Sao Paulo. And what we were able to see is that there is a strong correlation that can go until 100 kilometers far away from Sao Paulo. That can be related to meteorological forcing. Also, there is an influence of the urban plume, something that we have to analyze, the boundary of this influence, and also exposure to long-range transport, since most of these areas are also affected by transport from the south of the Amazon. So this just to give an idea about how aerosol variability over Sao Paulo is correlated with other regions around Sao Paulo. This is just, since we are interested in the influence of this urban plume, and one of the information that we will use to integrate it's satellite information. And this is a map of Sao Paulo macrometropole, AOD, from Mauris products, dark targeted products, at 3 kilometer resolution. And what I want to discuss here with you is that we have this strong AOD value, which definitely there is a signal from pollution, but also we believe that there is some sensitivity to surface corrections. If we look this is Vale do Paraíba metropolitan area, which is kind of linear metropolitan area, and we think that is not just pollution. Maybe there is a sensitivity to surface correction. Here is the region of Campinas, Piracicaba, which is strongly related with biomass burning, related to sugarcane. Okay, and we have this problem that satellite AOD has a largest uncertainty compared with ground-based remote sensing. And if we want to integrate satellite measurement with surface data, we have to improve this uncertainty from point of view of metropolitan areas of Sao Paulo. This is just a perspective, the whole state of Sao Paulo perspective. So we can see spots of high aerosol optical depth, which mainly here in this region that is strongly related to sugarcane production, and that may be related to biomass burning inside the state. But also we believe that there is a signature, an influence of signature of surface. These is our CTS sites, which measure in situ pollution. And there is, we can see that there are areas where satellite can report clear condition, which is consistent with surface measurement. But also there are areas where we have cleaner condition from surface point of view, but our aerosol is suggesting polluted condition. That's one of the reasons why we think that there is maybe a signature from sensitivity to the surface. This is just a map of surface reflectance from MODIS, and we can see that Sao Paulo is a bright surface, and that is an aspect that we have to take into account before we apply these satellite products directly to compare with surface data. That's because dark target product was not designed for bright surface. This is this is a comparison between this is comparison between IRONET, which is ground-based IOD retrieval, with satellite MODIS, in this case Terra satellite. Is for dry season, we can see that there is a, I would say, a good correlation between surface retrieval and satellite retrieval. Of course, the integration, the idea of integration of satellite with surface have to be discussed if this correlation is high enough. When we go to compare for wet season, we see that the correlation is not that good. So cloudy sky is still a problem for satellite retrieval, and most of the data that we have in terms of satellite are biased toward dry season or clear sky season. And we, of course, are interested in aerosol indirect effect, which will be a great contribution to the understanding of aerosol climate impact in Sao Paulo. Here's just to show you the seasonality of aerosol optical depth from MODIS and from IRONET. And in general, we can see that there is satellite and ground-based are able to reproduce this seasonality of aerosol optical depth, but we lack data here during the wet season, mostly due to clouds effect. Both satellite have different behavior. Here's for Terra, here is Aqua. This is something that we have to pay attention. Although the algorithm is the same, but satellites have different degradation response. I will finish here. What I would like to emphasize from the working group, which I'll be involved with, is cloud optical property characterization impact on IOD retrieval is to be a fundamental task to deal with. I would say that instead of use operational global product, we have to go for regional product. We have to develop a proper surface correction, cloud mask, and aerosol intrinsic property. We have already a contribution from Andrea Castaign studies that provide, but it's not an operational product. That's maybe a start to go for a regional product, product developed inside the context of Metroclima. For sure, aerosol indirect effect is still an open question for Sao Paulo, and we don't have studies focused on this indirect effect, and maybe this is a good opportunity to move on. Aerosol radiative property modeling, mainly IOD and absorption, will be a challenge for models. We have this plenty of data to assess model performance, and basically I will say that absorption will be a challenge, given this larger variability that we see for Sao Paulo. I think I'll stop here.
questions? We can start with the questions. I don't know if, because in the project we have many different aspects. It's from measurements at the surface, is also you trying to use the satellite data, the integrate the data from LiDAR also, and also starting the measurement of these fluxes of the greenhouse gases. We are starting, then we are trying to make this review of what we already have to start the measurements of the new compounds. Concerning the pollutants at the surface, we have data now for many years, but we are not. We have many open questions like this effect of these aerosols, and also the use of this satellite data. We try to have some good results, but not yet. Not can separate exactly the effect of the surface in the retrieval of the data. No? Then it's many open questions really.
I do have a quick question regarding the aerosol optic depths. You see the data from AeroNet, right? And have you had chance to intercompare that AeroNet aerosol optic depths with Maya product from Modis, which is available at the 1 kilometer by 1 kilometer resolution? It does much better job than regular level 3 Modis aerosol optic depths.
Actually, I'm not aware that this product is a global product. I think it is.
But it's public available since last June.
Okay. Yes.
They have probably 10 years data. Then it's much higher resolution and higher accuracy comparing to level 3 Modis aerosol.
Okay. That's nice to know. I'll check that. Nevertheless, I think we will still to work on these regional corrections, because as far as I know, the new product might have a urban correction, but essentially for United States case, which was generalized to other urban regions. And that's something that maybe we should be aware. But nice to know that there is this new product. I wasn't aware of that. But okay. Yes. Okay. 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 Thank you.
Questions?
Thank you. I was thinking maybe it's possible to compare our emission inventory maps with satellite data, and I don't know if you have do you have CO2 satellite data, and then we can compare maybe as an exercise, an important output in the Metroclima project. We can compare this satellite data with our estimates of emissions.
This is goal set from JAXA. Actually, there are 3 missions that we are focusing now. Should be goal set, OCO2, and Tropomi, okay, from Sentinel-5P, okay. So, as a satellite, it has global coverage, and they do have a product here that they do. I mean, they have this show graph. Actually, they put all together all the measurements, and they put also in EDGAR, which is an inventory for all emissions. And then you see they have something from South America. If you go there and zoom in, there are not too many things to look at, but it should improve. So, and then you can identify sources from the observation from not only JAXA, GOSAT, but also from other missions. Okay, and I did zoomed here for our region, and then they show like the trend. And then you have this sampling optimization, and then here you can see also some potential sources, like the cities, and in between when you have like an industrial site or something like that, and then you can identify the sources. So so the bottom line is, yes, it's possible from the observations to pinpoint the sources using the observations from the GHG emissions. Okay, and this is like an operational product, so you can retrieve that. So.
More questions or comments or suggestions? If they are. No?
I can't say you.
Well, I think maybe we can finish, and I'd like to thank everybody for the participation. This is a new project, as we said, and then it's open for people to participate. We have a lot of things to do. We are counting on the collaboration from our colleagues from outside also, and also the participation of all the students and people that are interested in participate. We are going to start the measurements, then we are going to have a lot of data to consider and to analyze. No, and thank you for all the speakers today. It was really a great day. Thank you, and I would like.